All right, I want to go ahead and start today by wishing everybody a happy Valentine's Day or a happy Singles Awareness Day, depending on your situation. But everybody gets a well wish today. So let's get started. Just a couple things, a little bit of housekeeping, going into next week because tomorrow is the end of the 6 weeks. We start the fifth 6 weeks on Monday. Your next quiz, like official quiz over the material, is going to be next Friday. Typically I do these on Thursday in the week, but I'm going to go ahead and move it one day ahead because if you're an IB student, then you know that today was the deadline for all the CAS material. So we have a meeting or final meetings with those students next week on Wednesday. So I'm not going to be in class. I'll have something left for you to do. But you'll have your quiz over this material a week from tomorrow. It's a little ways out. Tomorrow you'll get your homework assignments. In fact, we should be able to finish the assignment, or not the assignment, the notes within the first 10-15 minutes tomorrow, I'm hoping. And then the rest of the period, I'll just give you guys to go ahead and start working on the assignment. It'll be due next week, and we just see how far we're able to get. The only other thing, remember, next week, every day that I'm here next week, unfortunately we won't do one on Wednesday, but what are we bringing back? Happy minutes. Okay, so every day we're going to be solving a trig equation, so they're not going away just yet. Real simple one where you just isolate the trig functions all the way to using an identity to replace a portion of the equation. So I'll start off recording them as daily grades, then homework, then quizzes. So, be looking at your notes, come in if you have any questions on that. I think that's all I have. Does anybody have any questions? Nope. Okay. Then this is what we started talking about yesterday. We were talking about vectors. Now, the clip I showed you of Despicable Me, where Vector defined what a vector is, that is really accurate. It's a mathematical quantity represented by a arrow that has both direction and magnitude. Oh, yeah. Okay. I can't do it like he does. But there were a lot of terminology, vocabulary words that we introduced yesterday. The vector itself looks like an arrow, but where it starts, we call that the tail or the initial point. The arrow is where it ends, or we call that the terminal. Okay. And there was also one other one that was super important to us. What does standard position mean to a vector? What's on the origin? The what? The initial, there we go, the starting point. So if the vector is slid or translated across your grid so that the initial point is on the origin, that's what we call standard position. And again, it's one of those ideas in mathematics you just want to be very careful about, because when we say standard position, originally we're talking about rotating from the positive x-axis, especially when it comes to trigonometry. So when we're talking about vectors, that's what standard position refers to. And then we also talked about scalars, which are measurable quantities, and we did some examples of those. And then we moved on to component form. Now, component form works just like an ordered pair. The A value moves you horizontally, depending on sign. The B value moves you vertically, again, depending on sign. But this is instructions on how to get from the initial point to the terminal point, horizontally and then vertically. Remember, we were looking yesterday, we created a lot of right triangles. The only exceptions would be if the vector is horizontal or vertical, then one of your values is going to be 0. Okay, but let's see, I think after that, then we started looking at some of these graphically, and I believe we're ready to do some algebraically. Okay, so let's get right into it. So if I have a vector v whose component form is AB, and a vector w whose component form is CD, okay, well, here's some operations that we want to go ahead and be able to apply to component form. So adding or subtracting vectors in component form is super easy. You add or subtract the x values, the horizontal distances, and then you add or subtract the y values, the vertical distances. Okay. If you have a scalar value k that you want to multiply against a vector, okay, a component form, you just distribute it. So one step they didn't show here, if I have some kind of scale value k, and I'm going to multiply that against a vector in component form AB, well, you just go ahead and distribute that. And that's where they got the KA and then the KB. And then if I add a vector to the 0 vector, 0, comma 0, it's still going to give me the original vector. In fact, that reminds me of another vocabulary word. We were using the triangle method yesterday, right? So this third side that represented the answer we were trying to find, what did we call that? Started with an R. The resultant. There we go. We called that the resultant. Yes. Okay, well, let's just get right to it. So A, I want to take -3, that's my scalar value, and I want to multiply it by vector u. Okay, so here is u right here. So I'm going to say -3 times -3, 8. Okay. Well, all I'm going to do with that -3 is just distribute like we did that k a moment ago. In fact, what are my values? It would be 9 and -24. There you go. Okay, all I did was distribute that -3. Now, think graphically when we're looking at these changes to the vectors, multiplying it by 3, well, what's that going to do? It's going to make it longer. Yeah, it's going to make it larger. So it's going to triple the magnitude, right? But what's the negative going to do to it? Like we saw yesterday when we were subtracting vectors. It's going to change the direction, the exact opposite direction. It's still going to be parallel to what he was, but it's almost like 180 degrees in the opposite. The initial and the terminal are going to flip. Okay. Well, let's take a look at B. I want 2 times vector u minus 3 times vector v. Okay, so I'm just going to go ahead and first plug in the component forms of those vectors. So 2u would be 2 times the -3, 8. Okay, then I want to subtract 3 times vector v, 5, 2. There we go. Okay. Now here's the thing that people always ask, and it actually really doesn't matter. You could leave this as subtraction and simply go ahead and distribute the 3, or you could change it to plus and then distribute the -3. So really it's your choice whether you want to go ahead and take the negative with it or not. What would you guys like to do? You do want to take the negative? Okay. Then let's go ahead and say we're going to distribute the entire -3. Now, over here, we're just distributing a 2. So what would that be? Okay, so that is me -6, 16. And now because I'm taking the negative with the 3, it's now plus. In fact, plus what? -15, -6. There we go. Okay. So it's kind of like you're still subtracting, but you're adding the opposite, which is exactly what subtraction is. Okay. So again, when you add or subtract vectors, you just add or subtract the x's and the y's. So what is -6 plus -15? -21. Now what's 16 plus -6? 10.
Oh, wait. Oh, my bad.
Okay. So 10. There we go. So that would be the vector that represents 2u minus 3v. So that's not too bad, right? Okay. Now, I do want to go ahead and make a connection with what we did yesterday. I want to take these two vectors, u and v, and I actually want to go ahead and show this, just like we ended class yesterday. So I've already got this up, and you don't have this on your paper, and that's okay. So I've already got u and v. This is u, this is v. They're in standard position, right? Okay. I want to show that 2u minus 3v, we just found it to be -21, 10. Okay. Now this one actually really sets itself up. I don't have to do a whole lot, but I am going to use the mouse to make this go a lot faster. So you'll notice for each of these two vectors over here, like u, I've got a vector that is in the exact same direction, same magnitude, right? Okay. Same thing when it comes to vector v. Same direction, same magnitude. So here when we say magnitude, we're talking about the distance, okay, the length of the vector. All right, well, let me go ahead and erase this very quickly. Let me get this out of here. So I want to double u. So I'm just going to take this vector of the same length, and I'm going to attach them end to end. So this right here, there's the terminal side, and this would be 2u, right? Okay. Now, we actually just talked about this a moment ago. The -3v, pretend this was plus -3v, so I'm going to stretch the magnitude of V by a factor of 3, just like that. Now this is where the terminal side would be, but what's the negative do? There you go. It changes direction. So, oh, that's not what I meant to do. Sorry. The terminal end would be right here. So this would be negative 3V. Now, you remember yesterday when I said we wanted to go ahead and use a particular figure? What method was I using? What figure was I creating? A triangle method. Well, when you first use these vectors to create the two sides of your triangle, the resultant, the answer you're looking for is the third. But what was the one rule I said about the first two sides? There you go. You can only put a terminal end with a initial end. Okay, when you're first putting the two vectors together, you can't put two terminals together. You can't put two initial together. Now, when you draw the third side, your resultant, that's perfectly fine then if two terminal or two initial come together. Okay. In fact, let me go ahead and draw it. The resultant, not what I meant to do. Let's do this. Okay. Going from here to here, that's the resultant. This would represent the 2u minus 3v. Just like we were doing yesterday, right? Now, the terminal side would be right there. Okay. Now, remember, component form tells you direction and distance, horizontal and vertical, how to go from the initial to the terminal. So let's see if we were actually correct. To go from this point right here, okay, I should need, according to this, I should have to move 21 units left and then 10 up. And that should get me to the terminal of the resultant. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Does that look like it's even? And then from there, I'm going to go the 10 up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So see, I went 21 left. I went 10 up. We are absolutely correct in what we got. Okay. Now, at some point, you're going to have to go ahead and decide. When we do our application problems, I'm still going to go ahead and show you how to work them graphically, because I think, there is a level of importance to it. But after a while, I would really just encourage you to use the algebra. It's very straightforward. It's very fast. Okay. Not a lot to it. Does anybody have any questions about what I did here? Okay. All right. Well, let me go ahead and erase this. Let me get rid of what I don't need. Okay. Let me delete that. Let me get ready for the next class. Okay. Okay. So back to the operations. So we've taken care of A and B. So now C, I don't know what it's asking me. Magnitude. When you see the double bars, that means you want to take the magnitude, okay? Now, you'll notice it wants the magnitude of 2u plus 3v, or minus 3v. Well, that's exactly what we found here. Remember, your component form, okay, the horizontal is your A, the vertical is the B, right? Does anybody remember what's that formula for finding the magnitude if you have component form? I keep forgetting it. Square root of what?
A squared.
There you go. It's the square root of a squared plus b squared. The horizontal distance and the vertical distance from your component form. So I'm going to go ahead and do this. I'm going to put the component form in between those bars. Okay, just like that. So I know negative 21 is the horizontal, the A, as I just showed you. 10 is the vertical, the B. So we just plug in. So this is the square root, negative 21 squared plus 10 squared. So what's a negative 21 squared? A little higher. 441. There we go. Now that spasm I was doing with my hands makes a lot more sense. So, 4, 4, 1.
Oh,
That's what I was trying to do.
I just saw
Sorry.
it.
And 10 squared, 100. So this is the square root of 541. There we go. Now this one, that radical is not going to simplify, so we don't have to worry about it. Okay, so in this case, what we're talking about, the length of the vector that we just drew would be the square root of 541 units, if we're talking about magnitude and length. But remember, magnitude could represent a variety of ideas. Most notably for us, again, probably force when we do some physics problems, or even speed. Okay. All right. Let's take a look at this last one right here. Again, what do those two bars mean? The magnitude, but it wants the magnitude of u minus v. Okay, so let's see if we can get somebody up here to help me out. I'm going to go ahead and set this up for somebody. I'm going to draw the bars. So u was negative 3.8. And I want to subtract v, which was 5.2. Okay. So all we have to do is subtract the vectors and then find the magnitude by applying the formula. So who would like to come on up and help me with that? Okay. Random number generator. Number 6 was the second period person. I got 20. 18, 19, 20. That is Rhett. Okay. Rhett looks super excited to come up here. Okay, so he immediately gets the component form. He says negative 8, 6. And he goes right into the formula. So negative 8 squared plus 6 squared. Square root of 64 plus 36. Square root of 100, which is 10. There you go. That's the magnitude of that vector. Or I should say the difference of those vectors, whatever you wanted to call that. Perfect. Thank you. Anybody having problems? Anybody confused? Not sure where we're getting any kind of number from? What do we think about vectors so far?
They're cool.
They're cool? They're simple? Okay. They look easy? They're really not going to get that much more difficult. Huh?
They're really essentially just the slope of a line with restrictions on each end
Yeah.
for length.
In a manner of speaking, yeah. Okay. All right. Well, let's move on. Let me go ahead and erase this for the next class. Let's see. What do we have next? Okay, unit vectors. Okay, so if v is a non-zero vector in the plane, then the unit vector is a vector in the same direction as the original vector with a magnitude of 1 and is given by, now this one's a little off. It starts with vector u, but then it changes it to v, but it should be the component form of the vector divided by the magnitude of the vector. Okay. Or if you just want to change that to v, I mean, that's completely up to you. Okay. So the idea is really simple. It's just a very straightforward formula that you're going to use. But the idea is, let's say if I have a vector, okay, maybe, okay, u, whatever you want to call it, whatever direction, and let's say his magnitude is 10, just like the previous one. So the magnitude of u is 10. I'm just kind of, spitballing here. So what we're looking for is a vector that goes in the exact same direction, but has what magnitude? Yeah, so if we're talking about magnitude in terms of length, if this entire length of the vector is 10, then I'm looking for a vector that goes in the exact same direction, but is just 1 unit long. That's why we call it the unit vector. Is everybody okay with that? Okay. So let's get right to it. Here's an example. Find the unit vector and the direction of v equals negative 5, 15. Okay. So according to this formula, I'm going to take the component form, negative 5, 15, and I'm going to divide it by the magnitude of that vector. So negative 5, 15. So where do you think the first place I should start is going to be? Got to find the magnitude. Okay, what is that again? I keep forgetting the formula. Square root of a squared plus b squared. But you're right, it does come from the Pythagorean theorem. So component form always gives me a and b. Okay, so the magnitude of v is equal to the square root. Well, we have negative 5 squared plus 15 squared. Okay, so negative 5 squared, 25, plus 15 squared, 225. So this is the square root of 250, and this one will simplify. 5 times root 10, because it's 25 times 10, 25 being a perfect square. Yes, so 5 square root of 10. That's the magnitude. Is everybody okay? All right. So now I'm going back to this formula. So I'm going to take that negative 515, the component form, and I'm going to divide it by the 5 square root of 10. You will have to rationalize, yes. Jeez, I'm dead. All right, well, let me go ahead and show you something. The way I typically think about this, if you have the component form divided by this magnitude, then you just want to divide each of these distances by your magnitude, the 5 square root of 10. Another way to look at it, you could rewrite it, because it is a fraction. You could just say 1 over 5 square root of 10 times negative 515, and then just think of it as distributing that. However, it's easier for you to see, okay? Completely up to you. All right. But I just like to go ahead and divide. Hello. Oh, it is for... Oh, he's not here today. I'm sorry. Cool. Oh, that's sad. Savion had a crush, but he wasn't here. Oh. Well, I'm sure he'll still get it. Is he here tomorrow? No? Man, that's pretty fast for only a couple of days. True. Okay. All right. Negative 5 over 5 square root of 10, comma, and then 15 over 5 square root of 10. There we go. And this is what Christian was talking about. You want to simplify and then rationalize.
So it would be like,
So those are going to cancel. That will reduce. So what would you say it is, sir?
I was thinking it was going to be like -1 over root 10.
It is negative 1 over root 10, but let's rationalize that.
Oh, okay, so there's just going to be root 10 over negative root 10
Negative
over
square root of 10 over 10, comma. Now I need 3 over square root of 10 rationalized.
3 root 10.
3 square root of 10 over 10. So there you go. There's your unit vector. So again, let me kind of show you what this means. The vector v was negative 515, right? Okay. So I've already got this one set up. Okay. Here's vector v. It was negative 5. So from the origin, I went negative 5 left, 15 up. Okay, it's in standard position. This is the unit vector that we found. Well, notice it does go in the same direction, right? Because this one has me going left and then up. Well, this one has me going left and then up as well. If you were to go ahead and approximate these answers, okay, negative square root of 10 over 10 comes out to a negative 0.32 roughly. And then 3 square root of 10 over 10 comes out to about a 0.95. Okay. So if I were to go ahead and graph that from the origin, if I go left, negative 0.32, but then I went up 0.95, I mean, we're talking about right there. It's very tiny, but that's a unit vector in the exact same direction that just has a magnitude of 1. That's what it's doing. So it's kind of tiny. I'm sorry I couldn't find one. I had to do that very quickly this morning before the bell rang. But is everybody getting the idea? Is everybody okay with that? Okay. Good, 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 good. Now, we're not done with the problem yet because it said something else. What did it say? Okay. Then verify that it has a length 1. What is it talking about? How would I verify the length of this? What do we call that? What's another word we've been using? Starts with M. Magnitude. So I want to be able to take the magnitude of this. Remember, this is A, this is B. What's that formula again? Square root A squared plus B squared. So if I apply these values to that formula, it should give me what? Should give me 1 if we're correct. Well, let's see. The square root of negative square root of 10 over 10 squared plus 3 square root of 10 over 10 squared. Okay. Well, let's see here. We know it's going to be positive. What happens when I square a square root? Okay, so those cancel, so that would just be 10 over 10 squared. 100, so this first one should become 1/10. Right? And then the next one, we square the 3, we're going to get 9, times the square root of 10 squared, well, that's just 10 over, again, 100. So that's going to be 9/10. Whew, almost got 2 tenths in here. Okay. So what is 1/10 plus 9/10? 1, and the square root of 1 will give me 1. So yes, we did end up with a 1-unit magnitude vector. I'm sorry? Oh, you didn't hear my joke?
No.
I said 1/10, 9/10. We got lucky because it was almost 2 tenths in here. 2 tenths. Like you're anxious, you know, you're tense.
Oh.
2 tenths.
I thought
There
he
you
was
go.
doing it for that word, so I didn't get what that
No.
word.
I was like, you know, 2 tenths. Yeah, thank you. Thank you. Appreciate it. Okay, well, there we go. There we go. Okay. And I'm actually kind of surprised. I got to show this real fast, even since I'm recording. Did no one see, you know, what? Yeah, they see the love with the functions. No, did you see? You know what this? Did you see what this actually says right here? Yeah, the lesson and the 3. I love you. I heart you. Come on, it's in math. That's awesome.
You didn't do the heart part though. There's a
What's that?
feature that makes a heart.
Well, this one I found online. The other one, yeah, I did. Come on, nobody's commented on that today. I'm like, man. Thank you. Thank you. Now someone's going to quickly write that down and put it on their card to another person. So there you go.
Can I picture that quick?
Oh, seriously?
Yeah.
There you go. You gotta be all serious. That's a lot of cropping. Okay. All right. Okay, what are we doing next? Okay, so we did that. Okay, so linear combinations. Okay. Linear combinations, they're actually really straightforward. It's just another way of writing the component form that we've been dealing with. Okay, so here's what it says. The standard unit vectors of I equals 1, 0 and j equals 0, 1. So you know how we have the components A and B? A is the horizontal distance. You know, if I have a vector like this, then A is the horizontal, B is the vertical. Well, what we're saying is that I just represents 1 unit in the horizontal distance. Okay, J represents 1 unit in the vertical distance. Okay, that can be used to represent any vector. We call it linear combination of I and J. So this right here, if you see anything in linear combination like this, AI plus BJ, this is the same as the component form AB. Okay, like, let me go ahead and show this to you. Vector V here is given to me as linear combination. It says 2I minus 3J, right? So I can say the component form of that would simply be 2, negative 3. You just use the values themselves, the coefficients. Well, let me go ahead and show you. Let's start with 2I minus 3J. 2I minus 3J. Well, I, according to our definition here, is 1 unit horizontally. So 1, 0. Okay. Now we're going to go ahead and say minus 3J. 3 times J is 1 unit horizontally. So 0, 1. Now go ahead and do what we did just a moment ago. Somebody double 1, 0 for me. That would be 2, 0. Okay, right? 2 times 1, 2 times 0. Do we want to keep the negative here or use it?
Use it.
Use it? Okay. So let's distribute the whole thing. So that's going to make this a plus. Negative 3 times 0. 0 and negative 3 times 1. Negative 3. Now, how do I add vectors? Add the x's, add the y's. So I do end up with 2, negative 3. Okay. Linear combination is simply another way of writing this component form. It's just that we're saying our horizontal units are taken in 1 unit increments and the vertical are taken in 1 unit increments as well. Instead of A, the full length, and B, the full length. Does that make sense? That's all it is. Okay. So for these 3 examples here, we want to go ahead, given U is created using this initial point in this terminal, we already have V, write each of the following as a linear combination of I and J. So I want U written as AI plus BJ. But in order to do that, we got to know what the component form is. Does anybody remember what we did yesterday? If you have the coordinates of an initial and a terminal point, how do we get component form? Where do we start? Remember I said always, always, always what? Always, always start with the terminal. Okay. So for U, the component form, I'm going to take the negative 2 because that's the x in the terminal, and I'm going to subtract 3, comma. Then I got to keep going in the same direction for the y's. So what would I put here? 4 minus negative 5. Okay. So what's the component form for U? Negative 5, comma 9. There we go. Because minus a negative turns it to addition. Okay. Now, you remember what I did a moment ago where I went from 2i minus 3j to this right here? I could reverse the process, but you know A, you know B, just simply write out that linear combination. It would be negative 5 what? I plus 9 J. Because 9 is B. There we go. That's the linear combination version of that component form. Again, they are giving you the same information. Okay, it's just a different way of writing it. Personally, I like to go with the component form. I've never been very big on the I and J, but if you like it, please feel free to use it. Sometimes you are going to be asked to write your answers in that. Okay, so we do need to know about it. All right, now, vector W is going to be 2u minus 3v. Now this one here, again, you have your choice. We have both u and v in component form and in linear combination form, right? So I could use either one of those to find w. Okay, what would you like to use? Connor, what do you think? I'm sorry, what? No, what form would you like to work with? Would you like to work the problem using the component form or the whole problem using linear combination? Linear, okay, well, first one to choose that today, okay. So here's the thing, 2 times u, so I'm going to double the linear combination form of u that we just found. Negative 5i plus 9j, okay, minus 3 times the linear combination form of that. So I'm going to say 2i minus 3j. Because we want my final answer to be as a linear combination, right? Oh, hello. This is Juan. There you go. Hey, he's the lucky one. Hey. You don't have to. See, you could solve this as component form, or you could solve it as linear combination.
I mean, when you're using linear combination, though, you don't use the bracket.
No, it's just a different form, but it still means the same thing. So somebody double this binomial for me. So that would be negative 10i plus 18j. And then why don't we go ahead and actually, distribute the negative with it this time. So negative 3 times 2i. minus 6i
Uh, 9.
plus 9j. And you're just combining your like terms. Negative 10i minus 6i. Negative 16i plus 27j. There you go. Would anybody like me to go back, use the component form, and show you that you're going to get the exact same thing?
Yeah.
You do want me to show you that? Okay, let's do it. Okay. So remember the component form for you was negative 5, 9, right? Okay. All right, so let me erase this so I have a little more room. So I'm going to do the same thing. So 2 times u, but I'm going to use the component form. Negative 5, 9 minus 3 times the component form of v was 2, negative 3. Okay. Well, I'm still going to go ahead and distribute. So that's going to be negative 10, 18. Okay. And let's distribute the negative with it here. So this will become a plus. That would be negative 6 and 9. Do you notice anything? Aren't these the exact same values as these over here? Yeah, it just depends on the form you want. And now just combine them. So negative 10 minus 6 would give me the negative 16. 18 and 9 would still give me the 27. And this component form is that as a linear combination. Okay, so whatever you feel more comfortable working with. Okay, absolutely. Good. Okay, the unit vector of W. Okay, now this one I am going to go with the component form. I just like to use it better. Okay, so what was the component form for W? Remember, this was the linear combination for W. Oh, no, not the formula, just the component form. So negative 16, 27. There you go. Okay. Is everybody okay with that? Okay. So now you were telling me the formula, you're absolutely right. If I want the unit vector, I have to take the component form of that vector and divide it by his magnitude. Well, we have the component form, but we need to know what the magnitude of W is to finish this one. Okay. So let's see here. The magnitude of W. I keep forgetting, what's that formula? Square root. So a squared, now remember, this is A and this is your B. Even in linear combination, that's your A, that's your B. Same thing. So negative 16 squared plus 27 squared. Okay, so we don't have calculators today, so let's see how well we can do. Negative 16 squared should be easy. That's 200 what? 256 plus 27 squared. 729. Did we use a calculator? Yes. And what's my final answer here? 985. There we go. Perfect, perfect, perfect. Okay. So now, let's go back to the formula. So I know the component form was negative 16, 27. I'm going to divide it by square root of 985. Okay. Now, I'll go ahead and tell you that you are going to have to rationalize, but 16 and 985 don't have any common factors besides 1. 27 and 985 don't have any common factors besides 1. So that can kind of speed things along a little bit. If I did have negative 16 over the square root of 985, what would that be rationalized? Or do I need to just write this out? So negative 16 root 985 over 985, comma, now 27 over the square root of 985. Square root 985 over 985. Okay. Now that's the component form, but it wanted the linear combination form. So this is A, this is B. What am I going to do? Basically, what am I going to attach to? Yeah, you just need the I and the J. So this would be negative 16 square root of 985 over 985I plus that ratio times what? J. Oh, we got another one. Hello. Thank you. Miriam. Miriam has way more candy in that big basket of hers. Is this all from the same person? No? Oh, she got multiple admirers. Damn. Okay. Okay, cool. All right, as far as the problem goes, any questions? All right, good. Well, there is one last thing I'm going to go ahead and show you today before we take off, and it is probably the most important formula we can use when talking about vectors. It's the direction angle of a vector. Because think back, a vector is only useful, it's only a vector if you have what two items? If you have a direction and magnitude. That's what this formula will immediately give you. The direction angle of a vector is the angle the vector makes with the positive x-axis. So we're rotating, okay, from the positive x-axis. But if a vector is in component form, this is what A and B are going to equal. A equals the magnitude times cosine of theta. B is going to equal the magnitude times the sine of theta. Now you remember what I just said, it's only a vector if it has both direction and magnitude. Well, this is a product of the magnitude and the direction. Okay, so it's going to give you the component form of that final vector. Now, the one I like to use is this one right here, the magnitude times the component form, but I go ahead and take it one step further. I distribute that across. So this is the formula I like to use. The magnitude of V times cosine of theta, comma, the magnitude of V times the sine of theta. We are going to be using him a lot, especially when we start looking at those application problems. Okay. Now, you may be wondering, well, why does A equal this? Why does B equal that? Well, I'm glad you asked. Okay. Let's go back to just normal everyday trigonometry. Okay. Let's say this is my vector V. Okay. So we have the magnitude representing the hypotenuse. What are the components now? What's the horizontal and the vertical distances we've been using? Yeah, but what variables when we deal with vectors? What two keep popping up? A and B, right? Remember, A is the horizontal distance, B is the vertical. Okay, there we go. So if I want to say cosine of theta, that's going to equal the adjacent over the hypotenuse. So A over the magnitude of V. Well, let's say I wanted to solve this for A. What would I do? I'd multiply both sides by the magnitude. So when those cancel, A equals a product of the two. And see, that's where my formula comes from. You could do the exact same thing for sine. Okay. So here we go. Write vector V as a linear combination of the unit vectors I and j if the magnitude of the vector is 4 and the angle measure is 30 degrees. So if you have this information, if you know the direction, basically the angle of rotation, and you know the magnitude, you can use those to immediately get your component form. And we've been using component form a lot, right? Okay. So here we go. V would equal, let's just use this right here. What's the magnitude? 4 times the cosine of what? 30, because we have magnitude and we have direction, comma, now I'm going to do the same thing, magnitude sine of theta. So 4 sine of 30. Okay. Now this should be pretty easy. What is cosine of 30 degrees? Oh, it's not 1/2. It is square root of 3 over 2. Now, Aiden, what's sine of 30? That's 1/2. There we go. Let me get this out of the way. So let's see here. What would 4 times the square root of 3 over 2 look like? Okay, there you go. So you'd simplify. So 4 square root of 3 over 2 would be 2 square roots of 3. And then comma 4 times 1/2. 2. So that would be the component form of V. If you know those two items, you can immediately use that formula. It's very useful. But it wanted what? Okay, it wanted the linear combination. So what would that be? to square root of 3I, because remember, this is A and this is B. So plus, yeah, I was putting B, 2J. There you go. Now, there's one other thing that I haven't mentioned. If you have the component form, but you don't know what the direction is, you can actually take tangent of theta equals the ratio of B over A, and it will provide you that rotation. In fact, because we are now out of time, do me a favor, somebody remind me tomorrow to talk to you about that. I want to show you that, then we'll go ahead and get in that last problem. Okay, so don't let me forget, I want to show you that tangent formula. Okay, very good, very good.